Okay, let's talk about vertical circular motion. Horizontal circular motion, we can take weight out of the equation. Once I get into vertical circular motion, weight matters. Ferris wheels, roller coasters, kids on swing sets are all common examples of the type of things you might encounter with this. Now, let's look at a roller coaster first. So I'm going to have a loop on a roller coaster, like that. And what I want to do is look at what happens at different parts. Let's look at point A over here. And what I want to do is draw a free body diagram, and I'm going to draw it right simply on the diagram. Now, we always know that there's an mg vector acting down. Now, since you're moving in a circle, there also is a force directed towards the center of the circle. Well, in this case, it's actually the normal force. It's a reaction force from the track that pushes you back towards the center of the circle. Now, if you were to look at the complete net force, this is going to be strictly towards the center of the circle. This is going to be straight down. The net force is going to be the sum of those two. Remember when we add vectors, we go tip to tail. So I redraw mg over here. That's my net force. And now, if I'm at point B up here at the top of the track, and I draw a free body diagram, again, mg is acting straight down towards the center of the circle, center of the earth, excuse me. In this case, the normal force is also acting straight down towards the center. Your net force would simply be the sum of those two. You'd add them up since they're both pushing into the center of the circle. So the net force is going to be strictly down in that case. Now, if I have this over here, what I'm going to have now is mg acting down towards the center of the earth again, but now the normal force is pointing into the center of the circle. The net force is going to be out there. So again, your net force is going to change as you go around that circle. Okay, let's take a look at, let's do a little bit of math. So let's encounter one now. Let's say I'm at the top of a roller coaster loop. And we're just going to do it all with variables. You have a certain speed v, you have a certain radius that you're going to be given to the problem, and of course you're probably also given m, and of course you always know g. So let's just leave it in terms of variables right now. First thing you want to do is draw a free body diagram. Always trust the free body diagrams. Don't try and memorize your way through specific cases. It's better to learn how to draw the free body diagrams and learn how to apply Newton's second law. Now, if I draw the free body diagram, there's a weight vector going straight down, mg. There's also an Fn that's also going to be acting down. Now, I don't know whether Fn is bigger than mg or not. I don't really matter, but the key thing is it's directed down. Now, I'm going to say down is positive, just simply because two of my vectors are pointing in that direction. It makes sense to do that. I'm now going to say the sum of the forces equal m times a. Now, since I'm moving in a circle, I know a. A is equal to v squared over r. It's the centripetal acceleration. Let's make that a capital R since that's what I used up there. It's a centripetal acceleration. Now, the sum of my forces, well, they're both pointing in a positive direction, so it's going to be Fn plus mg. Well, what I want to find out is Fn, I guess I should have stated that first, and then I want to find out the minimum speed to stay on track. Modern roller coasters have safety features, but what's the minimum speed you'd need if there was not safety wheels on it? So now I'm going to say Fn is equal to mv squared over r minus mg. So all I did was rearrange it there. Now, in order to completely solve it numerically, you're going to have those values, but you can do it in terms of just variables without that. Then plug and chug the values in. Values are only part of the question. Now, so for part B, now I want to find the minimum V. Now, the minimum V is going to occur when that normal force disappears. I have to have a normal force applying some downward force into the center of the circle. If I don't have that, then what's going to happen is I'm not pushing into the track, therefore I'm going to fall. So if the normal force is equal to 0, and that's going to be the minimum, then I have mv squared over r minus mg, so therefore I have mv squared over r equal to mg, and of course my m's cancel out, sorry about that, my m's cancel out, I get v squared is equal to r times g, v is equal to the square root of r times g. So that kind of allows you to solve it. Again, if you get numbers, then you can put numbers into it afterwards. Now, let's tweak it just a little bit, and here's where trusting the free body diagrams helps. What we're going to do now is go to the more modern type of roller coaster, in which you're actually sitting up here above the track, and it's on wheels. Okay, now, if we draw our free body diagram, mg is still acting down, it's always the case, but now the normal force is going to act up, because it's a reaction to the force. Now, if you take a look at that normal force, what we're then going to do and say is the fact that the normal force has to lose the battle, because I know that I'm accelerating downward, so the net force has to be downward. Now, I'm going to say down is positive simply because I know the net force has to be down. I'm going down. Now, this has to have safety wheels on it to make this work. Now, if we apply the same physics, the sum of the forces equal m times a. Again, we're moving in a circle, so a is v squared over r. So this is mv squared over r. The sum of the forces, now we have mg minus fn. When I then move fn to the other side to make it positive, now I'm going to get mg minus mv squared over r. So my normal force has changed a little bit to make it happen. Now, so this is quite a different ride. The normal force you're going to feel as a person, you're actually going to feel it on your shoulders in the shoulder harness. If you didn't have that shoulder harness on, you'd be in trouble. Now, if I go to the minimum V, something kind of neat happens here. The minimum V again is when Fn is equal to 0. And now all of a sudden I get 0 is equal to mg minus mv squared over r. Well, that reduces down to the same thing we had before. V is equal to the square root of r over g. So that's kind of neat. You can put numbers in it if you want to make it happen. Now let's look at a tension problem. This is another common type of problem you can see that involving this. Let's have a how about a 60 kilogram kid, 60 kg kid, swinging at, I'll tell you what, let's figure out how fast they're swinging. We're going to put them on a 3-meter rope. So they're on a 3-meter swing. They're sitting there like this, hanging their feet off like that. They're going wee like that. Now, I'm going to tell you that the drop from there to there is 1 meter. So in other words, they have swung 1 meter deep. What I want to know is V at the bottom. And I also want to know the tension on the rope at the bottom. So in other words, how strong of the cable how strong does the cable have to be in order to do it? Now, speed at the bottom, easiest way to do, energy. Again, if energy will do it, use energy equations. Up here it's all PE. Down here it's all K. So therefore I'm going to say mgh is equal to 1/2 mv squared. M's cancel out, really doesn't matter how big the kid is for this case. And I get v squared is equal to 2 times g times h. This one I have numbers for. So 2, 10 meters per second squared. Again, you can use 9.8 if you want. Times a height of 1 meter. So it's going to be, v is going to be the square root of 20. The square root of 20 is 4.47 meters per second. So that's how fast they're moving right there. Okay, now for part B, I want to figure out the tension in the rope. Now, as soon as I get to a force problem, I want to draw a free body diagram. So there's a kid sitting on a swing. Beautiful drawing. We know mg is acting down. In this case, T is pulling up. Now, is T going to be bigger or smaller than mg? It's got to be bigger because the kid is accelerating towards the center of the circle. So I would simply draw it bigger. Now, it doesn't really matter which way you call positive as long as you're consistent. Let's go with up positive, although it works just as well with down being positive. I'm now going to say that the sum of the forces equal m times a, moving in a circle, so therefore I know that a, so it's equal to mv squared over r. And let's do it all with variables first and then plug in at the end. Now, the sum of the forces, well, I'm going to draw the positive one first, so I'm going to go see T minus mg is equal to mv squared over r. Now, I'm solving for T. Move it to the other side. mg plus mv squared over r. Okay, now let's plug and chug and get an answer out of it. Well, m times g is going to be 600 newtons, 60 times 10, plus 60 kg times the speed of 4.47 meters per second squared divided by the radius of 3 meters. Now 4.47 squared is 20. We already got that. 20 times 60 is what, 1200? 1200 divided by 3 is 400. So this is 400 newtons. This is 600 newtons. This is 1,000 newtons. Guys, here's the key thing. Don't try and memorize your way through physics. Learn how to use the free body diagrams. Learn how to use Newton's second law. If you try and memorize your way through the course, number one, it's going to be boring. The challenge is the different ways we can work these problems out and make them happen. Hope this helped.